Good evening, everybody. I am Vibhu Singh from PowerTech Consultant. Today we start our webinar number 15. Let me share my screen with you all. So this is webinar number 15, and in this we'll study the book 3, chapter 2, that is electric motors. This is required for those who are also appearing for paper 4 as well. Now, what is motor selections? Motors are workhorse for any industries. So we need some motor for our operation for industrial drives. But how to select a motor? The prime technical consideration for selection of motor is torque, because it is supposed to give you some torque at a particular load. So all you know, one is maximum torque generated by a motor, that is a breakdown torque. That is another name is breakdown torque, and another one is the torque for requirement for startup and the torque during acceleration period. So there are three torques. One is starting torque, particularly like traction motor or particularly for belt conveyor, you need higher starting torque. But another one is maximum torque generated by motor, that is at optimal frequency, at optimal speed, what is the maximum torque that can be generated. And how the acceleration torque is, it should be very smooth, so that particularly for belt conveyor, the acceleration torque should be smooth. It will avoid spillage of materials. The second parameter for motor selection is duty or load cycles. That means if you switch on or switch off any motor frequently, then it will require uh, more thermal loading. That means the temperature rise will be more. But for a continuous rating machine CRM, which is running continuously for 24 hours, the thermal loading will be relatively lower. Now, in case of totally enclosed fan-cooled motors, the cooling will be insufficient if motor operates at speed below its rated values. Now, in case of TFC, it is getting cooled, the heat is being taken away due to rotation, due to speed of the motors. There is a fan attached. Now, if the speed reduces, then the fan operation will reduce, which will cooling will not be sufficient. So, duty cycle, load cycles, and depending upon the speed requirement, the motor can be selected. Now another one is ambient operating conditions. Now what, in which atmosphere the motor operates, whether it is dusty, whether it is corrosive, whether the temperature is very high, or you require a flame-proof type of design, or there is a restricted physical space. So these are the ambient operating conditions at which the motor operates. It also affects the motor choice. Then switching frequencies. Now whether it is manually operated or automatically controlled, so this is another one. Then frequent starts, stops of large component like compressors also results in large voltage drop. If a large compressor is there and you frequently stop and start, then there will be large voltage drop, which will create some instability in the power systems, and this may affect the nearby load, due to which frequent start stop and the nearby load in the vicinity, based on which the motor is also selected. Now, whether you require motor to be reliable or unreliable, so reliability is one of the prime consideration for motor selections. Inventory. Now, particularly, lot of industries have larger inventory, or some industries they don't keep major inventory. Inventory means the stock position of different size of motors. So what they will do, they will only keep limited number of motors with lesser inventory, but they can use different sizes for different rating. Let us say some 7.5 kilowatt motor failed, then they have a 10 kilowatt motor. Normally, as per industrial practice, they use that 10 kilowatt motor instead of 75 kilowatt motors. In case they don't have spare of 7.5 kilowatt motor. Though it will run, but this will affect your energy performance. So in order to avoid that, you should have shorter durations, shorter lead time, and sourcing of good industrial motors from a supplier who are nearby, so that your energy performance will not get affected. Price, yes, price is another issue. When you select a motor, we look for the lower cost of motors. But as you know, but energy efficient motor are relatively costlier. Now here, as an energy conservation perspective, one has to see that what is the life cycle cost. That means if the life cycle cost with lower efficiency, the life cycle cost will be high, because it will take very high current, the energy losses will be more, energy conservation will be more. So within a period of 2 years, you will there will be huge variable losses or variable cost, which will nullify the initial low cost of the a standard efficiency motor. But if you go for higher premium or super efficiency motors, what will happen? You might have incurred some incremental cost, but since the losses is low or efficiency is high, therefore it will take lesser input energy, due to which the lesser electric bill will be there, and you will be able to recover the incremental cost of that energy efficient motor within a period of 1 to 2 years or 2 years. So we should always select good energy efficient motor instead of standard efficiency motor. Now there are other points during selection of motor, what to see, what is the power turn at 75% of loading, and whether this is a meaningful indicator of energy efficiency, because motor normally runs at 75% of the loading. Then what is the reactive power or kVA drawn by the motor? Now some Indian standard 325 tells that the efficiency should have tolerance of 15% for 50 up to 50 kilowatt rating. But for above 50 kilowatt rating, the efficiency tolerance should be 10%. But in recent times, the industries also look for efficiency without any tolerances. Then there are a lot of standards on which the motor is selected or motor is procured. Two are Indian standard IS 8789, which talks about technical performance of standard motors. IS 12615 address the efficiency criteria of high efficiency motors. Now, in case of there are another IC test method, another one is IEEE test methodologies. So these are the international standards. But in IC, stray losses are assumed at 0.5%. In IC, losses are understated. That means it shows a higher efficiency. But in case of IEEE, the efficiency will be lowered because it reports a higher losses. So based on test certificate, you ensure test certificate along with procurement of motors. It might be routine certificate or a type test certificates. We have discussed in the earlier class what is type test certificate and what is routine test certificate. Now, what is the energy saving by motor replacement? Suppose you are going to replace your standard inefficient motor, or it has been owned, failed number of times. Now 4 times it has failed, you have to replace the motor. So you need to also calculate what will be your kilowatt saving by this formula. Kilowatt saving will be kilowatt output divided 1 efficiency of old motor minus 1 divided by efficiency of new motor. This formula you have to remember. So based on this kilowatt saving, you can calculate what will be your financial saving, what is the cost of top motor, and what is the payback period. So based on this, you can submit your note for approval for selection of higher good premium efficiency or super efficiency motors, which is worth for your investment. Now, as you see, these are okay. The power has gone, so I hope I'll be able to continue with this. Now, energy efficient motors, particularly if you see, this is the high efficiency motor, this is the standard efficiency motor. So for different motor kilowatt, the efficiency percentage is little bit higher for high efficiency motors. So if you can calculate, it is at 2 kilowatt motor rating, the efficiency will be around 78, but in this case it will be around 82. So normally 3 to 4% the high efficiency motor are more efficient as compared to standard efficiency. Why? Because they use low loss silicon steel, they use longer core. When you use low loss silicon steel, that means it is a CRGA, cold rolled grain oriented silicon steel, which has good permeability. The flux magnetizing current required will be small or will be lower. And longer core will, it will increase the active material. Then thicker, when you increase the active material, then automatically what will happen, the flux density or the flux density will reduce, and you will have lower magnetizing current. Thicker wire, it will reduce resistance, so I square R loss will reduce. Thinner lamination, it will reduce eddy current loss. Smaller air gap, so that magnetizing current does not have to travel much. So smaller air gap between starter and rotor. Copper instead of aluminum bars. When you use copper, you will get good efficiency, because your I square R loss will be lower. Superior bearing, smaller fan. These are the, because of this technology, your standard or this high efficiency motor have good efficiency. Now, as I told, this we have already studied starter and rotor I square loss. What are the losses associated with any motor? One is starter and rotor I square loss. Typically, it is 55% to 60% of the total loss. Now, these losses are due to resistance of the starter and rotor. Now, these losses are function of conductor resistance. Because of the conductor resistance and based on the load current, these losses is a function of these two values. So if you reduce the resistances, then automatically your I square R loss will reduce. So suitable selection of copper conductors then will also have reduced I square R loss. Now motor operation closer to synchronous speed, because if the slip is there, then it will lead to higher rotor I square R loss. So if your motor operates closer to synchronous speed, then your slip will be reduced. So which will reduce your rotor I square R loss. Core loss is basically two types. We have also studied in transformers, in motors. One is hysteresis loss and one is eddy current loss. Now these are due to magnetizing of the core. Now this core loss can be reduced by reducing a flux density, by utilizing low loss grade of silicon steel laminates, and the reduction of flux density can be achieved by suitable increase in core length of the starter and rotor. So you can increase the core length, you can use good quality steel like silicon steel, and eddy current losses can be reduced by going for thinner laminations. If you go for thinner lamination, the circulating current will find higher resistances, so due to which the current will be low, and the resistances because of this thinner lamination, the resistance will increase, due to which eddy current loss will be low and losses will be low. Friction and windage losses, it is due to bearing frictions, windage, or circulating air losses. Whenever that the motor rotates, there is a fan is associated, due to which it also some air resistance is occurred. This is known as windage loss. Now this is around 8 to 12% of total loss. These losses are independent of load. They don't depend upon the loading of the motors, but whereas starter I square loss or rotor I square loss are depend upon the load. Another loss is stray load loss. It is the square of load current and caused by leakage flux induced by load current in the laminations. That means it is the leakage flux. This stray load loss is almost 4 to 5% of total losses, and this is due to leakage flux. Now, this loss can be reduced by careful selection of slot numbers, tooth, slot geometry, air gap. So these are the power loss area, and these are the efficiency improvement program for any motor, due to which the efficiency increases and by reducing these losses. So one is iron loss, that is eddy current and hysteresis losses. Starter I square loss, it can be reduced by more copper, large conductor, so R will go down. And rotor I square loss, by going for good conductor, copper conductor in rotor bar, by reducing resistance of rotor. Friction and woodage loss, by going for low loss fan design, so that your air movement will be lower. But you have to optimize, you need also fan to cool the motor, otherwise heat generated within the motor cannot be dissipated. Stray load loss can be optimized by quality control and by good selection of slot numbers and all. So energy efficient motors have little bit higher efficiency, 3 to 7%. Particularly, we have done some exercise in i3 motor in which the efficiency are almost 10% higher. Now, what are the factors affects the energy efficiency or motors? There are major hardly 2-3 factors which is affects your motor efficiency and motor losses. One is power quality supply. Now you need good quality of input power. Without that, your motor performance will not be good. Now, if you see, BI standards specify that motor should be capable of delivering its rated output with a voltage variation of plus minus 6% or frequency variation of plus minus 3%. That means I need good voltage and good frequency so that my motor performance will be optimal. But in Indian conditions, you normally don't achieve this voltage variation. Sometimes the voltage widely vary. In the rural area, you get the voltage of 200 volt or 150 volt, 160 volt. So at low voltage, the motor performance deteriorates. So voltage fluctuation can have detrimental impact on motor performance. Now, this is a table which shows that if the voltage increases, what will be the effect on starting and maximum torque, synchronous speed, slip, full load speed, what will have its effect on efficiency, power factor, full load current, starting current, and maximum overload capacity. That means if I increase the percentage of voltage, if I increase the voltage or reduce the voltage, what will be its impacts? So you need to just go through it. It can understand how the voltage varies, then how the efficiency varies. Now coming here, if voltage increases, at 100% load, you don't have any small increment in efficiency. But at 75% load, the efficiency reduces. But whereas if voltage is using 90 to 110%, there is no major impact of efficiency at 75% load. Whereas if it is 50% load, it will go down if you increase the voltage, and it will go up if you reduce the voltage. Similarly, power factor, if you increase the voltage, power factor goes down. But if you reduce the voltage, power factor goes up. Now, so this and frequency, this is the variations on efficiency and power factor and your slip. So you may have to remember this table for answering your short questions. Now, low end power factor improvement can be done by putting power factor capacitors bank, or you can also improve good voltage by minimizing the line length or cable size, or going for higher size cable or higher size line from substation to motor terminal. So this is the another way of increasing or improving the voltage profile for the motor power supply. Then you can also increase the tap of the transformer so that you will get a consistent and continuous low voltage can be avoided. You can get a good voltage at motor terminal. So these are the 3 ways by which we can improve the voltage in a motor terminal. Now, what is voltage unbalance? Now, let us say VAB. in a three-phase circuit, the line voltage are like this. One line voltage is VAB is 10 volt, VBC is 417 volt, VCA is 408 volt. Now, what is voltage imbalance? As per NEMA, National Electrical Manufacturer Association of USA, it is the maximum deviation from mean of VAB, VBC, VCA. So, you have to calculate where is the maximum deviation. Now, from this figure, I can easily understand the maximum deviation will be the mean of VA, VB, VC. So, you can find out percentage voltage will be 417 minus 411.7, that is the maximum deviation from the mean of VAB, VBC and VCA. So from this, because what I have done here, I have to calculate the mean of this one. The mean is 411.7. Now from this mean, who is deviating highly? 470 is deviating highly. So 417 minus mean divided by this mean will give you voltage imbalance. So voltage imbalance is 1.29%. Now unbalance, why voltage unbalance occurs? Because the loading is not appropriate. In three-phase load, if you give unbalanced load, then automatically your voltage will be also unbalanced, because the potential drop will be unequal in each different circuit. So based on the potential drop, based on the current flow, because there are three different resistances or impedances are there in the three-phase circuit, due to which voltage and current unbalance will happen. So, and this is the effect of voltage unbalance on motor performance. The current will behave widely, the temperature will increase, because if you change your voltage pattern, if the voltage is unbalanced, there will be neutral current will flow, due to which the current increases, due to which the temperature or heat will I square R loss increases, and there is a temperature rise. Now this is the formula. What is the additional temperature rise if there is a percentage voltage imbalance is there? So normally it is 2 of percent square of 2 times of the square of voltage imbalance. So additional temperature rise will be 2 into percentage voltage imbalance. Now if the voltage imbalance is 2% for a motor operating at 100 degrees centigrade, so what will be your additional temperature rise? It will be 2% square, it will be around 4. So 2 into 4 will be 8 degrees centigrade. So this is a sample empirical formula you can remember. And when the voltage imbalance is there, because of temperature rise, the winding insulation life also deteriorate. So because insulation life deteriorates, so circuit fails, there is a short circuit chances are more, and so your voltage imbalance should not be there. Now what is motor loading? Motor loading is, that means at what percentage load the motor operates. Let us say 100 kilowatt motor is there, but every time it does not operate at 100 kilowatt, sometimes it operates at 80 kilowatt. So in that case it will be 80 by 100. Now how to calculate percentage loading? Input power drawn by the motor kilowatt at existing load. That means at the existing operating load, what is the input power drawn by the motor? Then the nameplate full load kilowatt or nameplate full load motor divided by nameplate full load motor efficiency. Why you have to divide efficiency here? Because you know nameplate full load kilowatt is basically the mechanical output. So what will be your electrical input? At rated condition, it will be our mechanical output divided by full load motor efficiency. So we get input rated kilowatt. And what is the existing or operating kilowatt? Input power drawn by the motor at the existing load. So if we divide these two, we will get percentage loading. So percentage loading can also be calculated by this: input power drawn by the motor at existing load divided by root 3 kV I cos phi. Voltage, current, cos phi is the power factor. Also motor loading can be calculated actual operating load of the motor divided by rated capacity of the motor. Here but loading should not be estimated as ratio of current, and you should not assume any power factor. This is another empirical formula. By these three formula, you can calculate motor loading. Actual operating load, that means mechanical load, and rated capacity. Now, how to do motor load survey? What are these are the, suppose in case of any motor, why motor load survey is required? If any industries, very old industries, number of motors are there, very inefficient motors is there, but it takes energy and losses are very high, winding failure has happened, now we need to change the motors. So you need to understand what are the motor size. Sometimes you don't know the nameplate, there will be nameplate will be missing, and you don't know the size of the motor, which motor to be replaced. So for that, for motor replacement program, you need to conduct motor load survey. So what are those methodology? First, we need to calculate sampling criteria. That means we cannot replace all the motors. Some motors will be operating very fine. So we need to sample. Within survey, we need to do some sampling. So it can be done based on utilization factor. That means hour of operation, or those who are operating continuously have to be given emphasis. Like crane motor, we should not give emphasis because it operates at a very intermittently. So those motor which is running continuously, they will be saving potentially more. Then sample repetitive basis. That means cooling tower cone, let us take those motor, or air or units, let us take that, or pumps, blowers. So depending upon the sample representative basis, we also need to do certain measurement or some loading study of those motors. Then conservation potential. You can think of which are 4 times or 5 times or 10 times wound, which have motor have failed measurably, or what is the machine side, where the load is fluctuating. So based on this conservation potential basis, you need to also do motor load survey. Then after sampling, we need to go to the motor, do certain measurement. In the measurement, we have to calculate what is the voltage, current, power factor, kilowatt, and also you need to understand what is the load side measurement. That means what is the flow, what is the pressure, if it is a pump, and what is the temperature, what is the speed of the motors, and what is the load size. So based on this, we can calculate what is the loading of the motor. Now we can calculate what is the kilowatt increase in current. So based, if the current increase is very high, that means it is winding is not proper, it is taking high current, that means high losses. So based on this measurement, it will give you an indication which motor to be changed. If it is very old motor, it can also be changed. Then after this measurement sampling, we need to know analysis of the motor. That is motor load on kilowatt basis. What is the total motor number? What is the total kilowatt drawn? What is the annual energy loss? What is the financial loss based on electricity bill? Now, if I calculate what is the new motor, what will be the new motor cost? What will whether I'll go for highly efficient motors? Then what is the total cost of the new motors? Now, based on the financial saving of the due to energy loss improvement program and cost of the project, I can calculate payback period. If the payback period is within 3 years, then I should go for those motor replacement program. So I need to calculate what is the scope for energy conservation, related cost benefit, source information, how I should monitor those motors, how I should utilize those motors for better monitoring for application of my model. So based on this, I calculate, I do a motor load survey and go for motor replacement program. With this, I conclude this portion of the motor. In the next session, we can take up the remaining portion of chapter 2 of book 3. With this, I conclude. Good night.